Welcome back to the deep dive. Today we're dissecting a paper that frankly challenges the prevailing orthodoxy of the last few years in AI development.
It really does.
Yeah, it's titled MCTS-R Enhancing Retrieval-Augmented Generation with Monte Carlo Tree Search.
It's a title that, it hints at a collision of two very different worlds in computer science.
Exactly. Because on one hand, we have the current darling of the industry,
Right.
Retrieval-Augmented Generation, or R.
Right.
That's the mechanism that basically lets an LLM look up facts. And then on the other hand, we have Monte Carlo Tree Search, or MCTS.
Which is the algorithmic backbone that made AlphaGo famous, nearly a decade ago now?
Yeah, almost 10 years. So it's this fusion of modern generative AI with really classical decision-making algorithms.
It's a fascinating blend.
And the headline result here is what initially grabbed my attention. The authors are claiming that by using this specific methodology, a 7 billion parameter model.
Which we consider pretty small these days.
Right, like local grade, run it on your laptop small. They claim it can outperform massive frontier models like GPT-4o on complex reasoning tasks.
Like a very bold claim.
It is, it's huge.
But it suggests that the bottleneck right now isn't necessarily just parameter count or, training data size. It's actually about the architecture of inference.
So wait, thanks.
Exactly. It's about how the model utilizes the knowledge it already has, or, crucially, how it searches for the knowledge it lacks.
Okay, so before we get into the weeds of the algorithm, and I really do want to get into the weeds today, specifically on those selection and backpropagation steps, let's frame the problem for you listening.
Good idea.
Why do we even need this? I mean, we have RAG, we have vector databases, we have semantic search. Why isn't giving the AI a Google search bar enough for these complex questions?
To understand why MCTS-RAG is necessary, you really have to look at the failure modes of standard RAG.
Where it breaks down.
Yeah. Standard RAG is essentially a linear process. We call it retrieve, then generate. You take a user query, you turn it into a vector, you find the top similar chunks in your database, you paste them into the context window, and you basically just tell the model to answer.
It's a one-shot deal?
Precisely. It's greedy.
Greedy meaning it just grabs what's in front of it?
Yes. It assumes that the initial retrieval was perfect. It assumes the documents it found are totally sufficient to answer the question.
Right.
And it assumes that the model can linearly reason from those documents straight to the answer without needing any intermediate steps.
Which, that's fine if I ask something simple like, what is the capital of France?
Sure.
But it completely falls apart if I ask a multi-hop question, something where you need to connect the dots.
Right. The paper actually uses a really great example to illustrate this. The question is, what is the government type of the country whose national anthem is Lamali?
Okay, let's break that down. A standard RAG system sees Lamali and anthem.
Right.
It runs a vector search. It probably finds the lyrics to the anthem, maybe a Wikipedia entry about the song itself.
Correct. But here is the trap. The document about the song might not mention the government type of Mali at all.
It just talks about the music.
Exactly.
Right.
It might just say Lamali is the national anthem of Mali.
Yeah.
So the model gets that document. Now it knows the country is Mali.
Okay, so it has half the puzzle.
But it has already finished its retrieval phase. It's stuck in the generation phase now.
Oh, I see.
It can't go back and say, oh, wait, now I need to search for the government type of Mali.
So what does it do? It hallucinates.
It hallucinates, or it guesses, or it just defaults to saying, I don't know, based on the provided context.
Because it lacks the agency to iterate?
Exactly. It doesn't have a loop. Now, there have been attempts to fix this with things like SAR or self-consistency reasoning, where you generate multiple chains of thought.
Right, that's the pure reasoning side of the equation. Just think harder.
Yes. But pure reasoning has its own massive trap. If I ask a model to solve a really complex chemistry problem or a question about a news event from yesterday, and the model simply doesn't have that information in its weights,
no amount of thinking harder is going to conjure up facts it doesn't know.
it's like a brilliant detective trying to solve a crime in a completely sealed, empty room with no evidence files.
I love that analogy.
They can spin a beautiful, perfectly logical theory, but without the actual data, it's just fiction.
So we have the librarian, which is standard argy, very rigid, very linear, brings you a stack of books and leaves.
Yes.
And we have the detective, which are these reasoning models. Brilliant, but sometimes completely factually blind.
And MCTS-RAG is the attempt to merge them. The core intuition here is to move from a linear chain to a tree.
From chain of thought to tree of thought.
Exactly. But with a crucial addition. It's not just a tree of internal thoughts. It's the ability to step out of the tree and fetch new external information dynamically.
Let's visualize this tree for everyone, because when we say tree search, we aren't just talking about a static data structure. We're talking about a decision space.
Think of the very start of the user's problem as the root of the tree. From that root, the model doesn't just pick one single path and hope for the best.
It explores.
It explores multiple possibilities. One branch might be, I need to define this specific term. Another branch entirely might be, I need to look up this historical fact.
And a third might be, hey, I actually think I can answer this directly from my memory.
Right. And the algorithm's job is to figure out which of those branches is the most promising before it ever commits to a final answer.
It's testing the waters.
It's deferring the final decision until you've explored the consequences of your intermediate thoughts.
Okay.
And the crucial innovation the paper highlights here is that retrieval isn't a separate phase anymore. It is an action.
That is a massive distinction, because in most RAG pipelines we see, retrieval is just pre-processing. You do it before the model even really wakes up.
Exactly. But here, retrieval is an active tool in the model's toolkit. It's an option in the action space.
So at any node in this tree, the model can choose to reach out to the internet.
Yes, it creates this really dynamic interplay between its internal knowledge, the parametric memory, and external knowledge, the non-parametric memory.
Okay, let's get into the actual methodology then. Section 3 of the paper outlines this action space. They define 6 very specific moves the AI can make, A1 through A6.
This is really interesting design choice because by limiting the model to these 6 specific actions, they are imposing a highly structured reasoning process.
They aren't just letting the model ramble in the prompt window.
No, it forces a cognitive structure.
Let's walk through them. A1 is direct answer.
Pretty straightforward. It just says, I know this fact. The capital is Paris. It uses this for low complexity steps where it's highly confident.
Got it. A2 is quick reasoning.
This is for logical deductions that don't require external data. So if A is bigger than B and B is bigger than C, then A is bigger than C.
Just pure internal logic.
Exactly. The model relies entirely on its internal weights for A2.
Then we have A3, which is decompose question.
This is your standard chain of thought decomposition, breaking a big, complex problem into smaller subproblems.
Like, to find the difference in age between 2 presidents, first I need President A's age, then I need President B's age.
It's exactly.
Now we get to the ARGI-specific actions. This is where it gets really distinct from older models. A4 is retrieval reasoning.
This is where the model explicitly generates a search query. It recognizes it has a knowledge gap, formulates a query.
Wait, it's not just reusing the user's initial prompt, right?
No, not at all. It's a targeted, specific query for that exact step in the tree. It fetches the data and integrates it into its thought process.
Okay, and then A5 is retrieval decompose. How is this actually different from A3, the regular decompose?
It's a nuanced difference, but it's a huge optimization. In A3, you just break the logic down into steps. In A5, the model recognizes that the sub-question it just identified is a factoid.
A factoid meaning something that can just be looked up.
Yes. It realizes it can be answered immediately with a search. So instead of creating a new branch that says, I need to find this out, and then searching on the next turn,
It compresses that into one single move.
exactly, it flattens the depth of the tree. It basically says, break this down and search for the first part right now.
I see. That's an efficiency play.
It absolutely is. It prevents the tree from getting too deep and unwieldy, which saves on token costs, and it severely reduces the chance of error propagation.
Because every extra step is a chance to hallucinate.
Precisely.
And finally, A6 is summarized answer.
This is the synthesis step. It takes the retrieved documents, the previous reasoning steps it took, and formats them into a clean, coherent final response.
Now, I want to pause on the retrieval aspect specifically, because when we say it searches, they don't just say, oh, throw a query at Bing and paste the first link.
No, they have a highly specific subroutine for retrieval. They call it the inner loop, and it consists of steps R1 through R4.
And this is critical, right? Because raw search results are incredibly noisy.
If you feed garbage into a reasoning tree, the whole process just collapses.
So R1 is query generation. We just touched on that.
Right, the model writes its own specific search terms based on the context of the current node it's on.
R2 is execution, just hitting the API.
Yes, getting the snippets back.
But R3, knowledge reflection, this seems to be the real filter here.
This is the discriminator. The model actually takes the snippets returned by the search engine and evaluates them before doing anything else.
It questions its own search results.
It asks, does this actually answer the specific query I generated? Is it reliable? Is it logically relevant to the path I'm on?
So it can just outright reject a search result,
Yes, and this is a massive upgrade over standard RAG. Standard RAG usually just blindly concatenates the top 5 results and hopes the model can sort it out.
which usually just confuses small models.
Exactly. MCTS-RAG explicitly filters out distractors, information that might be semantically similar, so it matched the vector search, but is logically irrelevant,
Wow. And then R4 is summary reasoning.
integrating only that verified useful fact back into the state of the tree.
The paper actually uses a chemistry example to illustrate this inner loop, the Grubbs catalyst problem. I think this really brings it home.
The question they fed it was, racemic 3-methylpent-1-amine is treated with Grubbs catalyst. How many possible products are there, excluding ethene?
Now, I am definitely not a chemist, but I can immediately see how a basic keyword search would completely fail here.
Standard RE searched for Grubbs catalyst reaction. It found a general textbook definition that basically said, this type of reaction typically produces 3 products.
So it just grabbed the number 3 because it looked like an answer to how many products?
Exactly, it matched the text pattern. But it completely missed the nuance of the word racemic and the specific stereochemistry of the starting material.
So how did MCTS-RAG handle that same prompt?
Well, it used the tree. It realized it needed to define the specific reaction for a racemic mixture first. It generated a targeted query for that.
Okay.
It found information about E and Z isomers and how racemic mixtures interact. But crucially, in the reflection step, that R3 step,
It checked the work.
it verified that the general rule of 3 products didn't apply to this specific chemical. It actually reasoned through the stereochemistry step by step to arrive at the correct answer, which was 6 products.
So it derived the answer rather than just trying to look it up in a table?
Yes, it used the lookup to get the rules of chemistry and then applied those rules to derive the answer. That is the System 2 thinking we are looking for.
That is incredible. All right, let's pivot to the engine itself. Section 5, the MCTS engine, because this is where the magic and, honestly, the computational cost happens.
This is the core algorithm running the show. It operates in a continuous loop of 4 phases: selection, expansion, simulation, and backpropagation.
Let's take these one by one, and I really want to explain this simply without the formulas. Let's start with selection. The paper mentions UCT, or upper confidence bound for trees. What is actually happening in plain English?
So imagine you are standing at the root of the tree. You have 3 branches you've already started exploring. One looks very promising, it has a high score.
Yeah.
One looks terrible, low score. And one you really haven't explored much yet.
The classic dilemma: do I stick with the winner, or do I see if the unknown path is a hidden gem?
Exactly. Exploration versus exploitation. UCT is simply an algorithm that balances these 2 urges. It gives a dynamic score to each branch. The score goes up if the average reward of that branch is high. That's the exploitation part. But the score also goes up if the branch has been visited very few times. That's the exploration part.
So it mathematically forces the model to go check its blind spots, but ensures it will eventually converge back on the most logical path.
Exactly. It guides the descent down through the tree until it hits a leaf node.
A leaf node being a point where it just hasn't generated any further thoughts yet.
Right. And that brings us to the second phase, expansion.
We are at the leaf. Now we need to grow the tree further.
The model looks at the current state of its reasoning and generates the next set of possible actions, those A1 through A6 moves we just discussed.
It says, from here I could search for X, or I could reason internally about Y.
Right. It literally creates new child nodes in the data structure.
Now, simulation. This is the part that I think always confuses people with tree search. We aren't fully answering the question out to the very end for every single branch, right? That would take forever.
Correct. In classic MCTS, like when it was playing AlphaGo, you might actually play the game all the way to the end to see who wins.
But with language models, generating all those tokens is way too expensive.
Way too expensive. So they often use a rollout or a heuristic evaluation. In this paper, they basically simulate just the next few steps to see if the logic is holding together.
They are essentially fast-forwarding the logic just a little bit.
They generate a quick draft of the future. Then they evaluate that draft. Does it make sense? Is it logically consistent? Does it seem like it's getting closer to directly answering the user's question?
And this evaluation produces a reward, a score.
Yes, a numerical value representing the quality of that specific path.
Which leads us directly to the final phase, backpropagation.
This is where the learning happens during the inference, but to be very clear for the listeners, we aren't updating the neural network weights here. We aren't doing gradient descent.
Right, we are not training the model. The model is frozen.
Exactly. We are updating the statistics of the tree itself. We take that reward score from the simulation, and we propagate it back up the exact path we just took.
We tell the parent node and the grandparent node, hey, this path we went down, it led to a really good result.
Yes. So the Q value, the quality value of those specific nodes increases.
So the next time the selection phase runs, when it uses that UCT formula, it will see that higher Q value and be much more likely to pick that path again.
Exactly.
Or, conversely, if the simulation was a complete disaster and made no sense, the Q value drops and the selection phase will actively avoid it next time.
Precisely. It builds a map of reasoning topography on the fly, customized for that one specific question.
Now, the elephant in the room here has to be latency. Running a tree search, generating multiple branches, simulating outcomes, backpropagating. This sounds incredibly slow compared to just a standard input-output API call.
It is slower. There is no getting around that fundamental reality. You are explicitly trading inference time for higher accuracy.
But the authors do introduce some efficiency hacks to make it practically viable, right?
Yes, they have a few clever tricks. First is parallel expansion.
This takes advantage of how GPUs actually work.
Exactly. GPUs love parallel tasks. Instead of generating one branch, waiting, then the next, the model generates multiple action candidates simultaneously in a single batch.
So it explores the breadth of the tree all in one go.
Yes. And they also use something called pruning.
Cutting off the dead branches so you don't waste time on them.
But they specifically prune based on what they call a similarity signal. This is really clever. If the model generates 3 different reasoning paths from a node, and they all diverge wildly into completely inconsistent logic,
That's a huge red flag.
it's a sign of hallucination or complete confusion. If the model can't even agree with itself across 3 simulations, it's probably entirely wrong.
So it just prunes them all.
Right. But if 3 paths are semantically very similar, that indicates stability in the reasoning. So they keep the stable ones and prune the outliers.
It's like a built-in consensus check mechanism while the tree is growing.
Exactly. And another really crucial efficiency point is retrieval necessity.
Meaning it doesn't search if it doesn't have to.
Right. The model doesn't have to hit the search engine every turn. If the UCT algorithm and the policy decide that action A1, direct answer, or A2, quick reasoning, is the best move,
It just skips the whole retrieval loop entirely.
it saves all those tokens and all that time. So for a really simple question, MCTS-RAG basically collapses back into acting like a standard LLM. It doesn't waste time doing a multi-step Bing search for what is 2 plus 2.
It's adaptive. It only invokes the heavy, expensive machinery when the problem's complexity actually demands it.
Exactly.
Let's move to section 6, final answer selection. So the tree is fully grown, the search is over, we have, say, 10 different leaf nodes at the bottom. Some say the answer is A, some say B, some say C. How does it actually pick the winner?
You might instinctively think, well, just pick the node with the highest individual reward score. Or maybe just pick the most common answer.
Like a simple majority vote.
Right. But the authors use a reward accumulation voting scheme. It's essentially a weighted vote based on the journey, not just the destination.
Break that down. How does it work?
First, they group the answers by meaning. So if one leaf says the number 6 and another leaf says 6 distinct products, those are grouped together semantically.
Okay, semantic grouping. Makes sense.
Then, they don't just count the number of leaves in that group. They sum up the reward scores of all the paths that led to that answer group.
Oh, I see. So an answer that was reached by 3 really high-quality verified paths beats an answer that was reached by 5 low-quality, really shaky paths.
Exactly. Quality over quantity. It explicitly prioritizes the answer that is supported by the most robust and verified reasoning process, not just the one that popped up the most often by random chance.
That feels like an incredibly robust way to mitigate the lucky guess factor.
It is. It forces the final system output to rely on the actual strength of its derivation.
Let's zoom out a bit and look at the broader landscape. Section 7 of the paper compares MCTS-RAG to other popular architectures. We've touched on standard RAG. What about self-RAG? That was a massively popular paper recently.
Self-RAG is a great approach. It trains a model to output reflection tokens. Basically, the model learns to critique its own retrieval in real time, but self-RAG is still largely a linear process.
It just retrieves at every step or at set intervals.
It's rigid. MCTS-RAG is much more flexible specifically because of that look-ahead capability we talked about in simulation.
Right. Self-RAG can critique the past, but MCTS-RAG can literally simulate the future.
It can pause and say, if I retrieve this specific document right now, will it actually help me answer the core question 3 steps down the line?
And what about REACT, Reason plus Act? That was huge for agents.
REACT was the fundamental precursor to most modern agents. It allows the model to reason, then act by searching, then reason again. But REACT is ultimately a single chain.
A single path through the woods.
Exactly. If REACT makes a wrong turn at step 2, say it performs a poorly phrased search or draws a logically flawed conclusion early on, the entire rest of the chain is poisoned.
It creates a massive error cascade.
And it has no structural way to back up and try again.
That is the core issue.
Yes.
Yeah.
MCTS-RAG solves this fundamentally with backtracking. If a branch turns out to be a total dead end, maybe the search returns absolutely nothing useful, or the reasoning leads to an obvious contradiction.
The MCTS algorithm simply abandons that branch.
It leaves it, goes back up to the parent node, and tries a different action from the action space.
It's essentially an undo button for AI reasoning. That is the fundamental mathematical advantage of the tree structure over the chain structure.
It allows for active error correction during the inference process itself.
Now we have to talk about assumptions. Every single methodology rests on some underlying assumptions. What are the authors assuming to be true here?
The first major assumption is that decomposition is always the right strategy for complex questions.
Is it not? I mean, breaking things down usually works.
Usually, yes. But sometimes, over-decomposing a problem can actually introduce noise. If you break a holistic question into too many tiny, disconnected parts, you might lose the semantic context of the whole.
You get the blind man and the elephant syndrome.
Exactly. You solve the subproblems, but fail to answer the actual prompt.
And the other big assumption has to be that reflection step, R3.
This is undoubtedly the biggest dependency in the entire system. The whole methodology relies heavily on the model's ability to accurately judge the utility of a search result.
Because if the underlying model, in this case a 7 billion parameter one, if it is too weak to realize that a retrieved document is logically irrelevant,
it will just let garbage right into the reasoning tree.
So the verifier function basically needs to be at least as smart as the generator function.
Or at least smart enough to recognize a bad text match. If that reflection step fails, the tree structure doesn't save you. It just amplifies the hallucination across multiple branches.
But looking at the benchmark results in the paper, they really speak for themselves. It shows the small 7B model beating GPT-4o in highly specific, complex domains.
It proves that a highly specialized, structured architecture can allow a significantly smaller model to punch way above its weight class. It is the ultimate process over parameters argument.
It hits a really fascinating sweet spot in the trade-off matrix. It obviously uses more tokens than simple R.
Oh, definitely.
But it uses far fewer tokens than something like R star, which just generates vast amounts of internal reasoning text without ever verifying facts. And the accuracy gain here is just immense.
It is efficient enough to be practically deployed, but thorough enough to be deeply reliable.
All right, let's do a full recap. I want to firmly cement this methodology in everyone listening right now. Let's literally walk through the life cycle of a single query from start to finish.
Okay, let's do it.
Step 1. The user asks a genuinely hard question. Let's say compare the GDP growth of the country with the Lamali anthem to the country with the Star-Spangled Banner anthem in 2023.
Step 2. The MCTS engine initializes. The root node of our tree is that exact question.
Step 3. The selection phase begins. It looks at the available actions, A1 through A6. It decides it needs to expand.
It likely chooses action A5, retrieval decompose. It splits that complex question into 2 subtasks, identify country for Lamali and identify country for Star-Spangled Banner. And it immediately initiates a search for those.
Step 4. The retrieval loop runs. R1 through R4, query generation, execution. It hits the Bing API and gets the results.
Step 5. Reflection, that R3 step. It checks those results critically. It says, I found Mali for Lamali and USA for Star-Spangled Banner. These look solid and factually reliable. It summarizes them.
Step 6. Expansion. Now the tree has 2 new verified branches populated with this knowledge. The logical next step is to formulate the next queries. Find GDP growth for Mali 2023 and find GDP growth for USA 2023.
And then it simulates this path. Maybe the search for Mali GDP 2023 returns ambiguous or conflicting data from different sources. The simulation score for that specific path is low.
Backpropagation. It sends a mathematical signal back up the tree. This path is shaky, don't trust it.
So the selection phase triggers again and tries a different branch. Maybe it tries action A4 to generate a more specific query, like Molly, World Bank Economic Report GDP 2023 instead. This works much better. High reward.
Step 7. It prunes any branches where it started hallucinating numbers that didn't match the retrieved search results. The similarity signal cuts off the bad logic.
Step 8. It finally reaches the leaf nodes. It aggregates all the valid non-pruned paths using the reward accumulation voting scheme. It sees that the path leading to the conclusion Molly was X%, USA was Y% has by far the highest cumulative confidence.
Step 9. It uses action A6 to construct the final clean response and delivers it to the user.
All automatically, all iteratively, and most importantly, all verifiably.
It really creates this profound feeling of the AI showing its work.
Which, if we are being honest, is the holy grail for enterprise AI adoption right now. You cannot put a black box reasoning engine in front of a corporate customer or a medical professional. You need a verifiable audit trail.
And the MCTS tree literally is the audit trail.
Exactly.
So we've arrived at the big picture. We've completely unpacked the engine. What does this methodology actually mean for the future of AI development over the next few years?
It firmly reinforces the idea that we are actively moving into the era of System 2 thinking for artificial intelligence.
Explain that distinction for anyone who hasn't read Daniel Kahneman.
Sure. System 1 thinking is fast, instinctive, automatic. That is basically what standard LLM text generation has been up to this point. Next, token prediction. It just flows like a rapid stream of consciousness. System 2 thinking is slow, deliberative, logical, and calculation-based.
It's stopping to actually think before speaking.
MCTS-RAG is effectively an architectural imposition of System 2 thinking onto a base System 1 model. It mathematically forces the model to pause, reflect, verify against reality, and plan its next moves.
And the massive implication there is that we don't necessarily need trillion-parameter server farm-sized models to solve the absolute hardest problems.
We might not. We might just need smarter cognitive architectures wrapping around smaller, highly efficient models. This methodology democratizes high-level reasoning.
That's a huge point.
You could theoretically run a very potent reasoning agent on local hardware, provided you just have the compute time to let the tree search run its course.
That's a fascinating paradigm shift. Moving from purely scaling laws, just make the brain bigger, to architectural laws, just make it structure its thoughts better.
And crucially, it reduces hallucination not by trying to train on more data, but by dynamically verifying the data it retrieves in real time.
I want to leave everyone listening with a final thought to really chew on today. We've spent this entire time discussing how a small 7B model uses this tree search to systematically beat GPT-4.
Yes, we have.
But imagine the counterfactual. What happens when we apply this MCTS-R architecture to the massive frontier models?
Right.
What happens when a model like GPT-5 or Claude is given the structural ability to run a Monte Carlo tree search over its own already massive reasoning capabilities?
That is the truly provocative question here. If a small model becomes a localized genius with this method, a genius-level model might become something entirely else.
It's wild to think about.
We could legitimately be approaching a level of automated research and multi-step problem-solving that fundamentally exceeds human capacity, simply because humans cannot hold a reasoning tree that deep and that wide in our biological working memory.
We can hold maybe 3, maybe 4 branches of a complex problem in our heads at once. This system can hold and evaluate thousands simultaneously.
It strongly suggests that the future of AI isn't just about knowing more raw facts, but about being able to flawlessly navigate the search space of solutions with literally superhuman precision.
A completely sobering and incredibly exciting thought. Honestly, it makes you wonder about your own human decision-making process. Do you have a strict knowledge reflection step? Do you actively prune your own bad ideas before you say them out loud?
I think most of us could probably use a little more UCT in our daily lives.
I think that is a perfect place to wrap up. Thank you so much for joining us on this deep dive into MCTS-RAG. It is dense, it is highly technical, but I genuinely think it is the shape of things to come in this industry.
Always a pleasure to be here.
We'll catch you on the next one.